I also want to mention Gottfried Wilhelm Leibniz, um, because he did the same invention as Bernoulli. He also invented or discovered Bernoulli's law, but it is named after Bernoulli because he was um, sometimes a law, for example, Newton's law is also called after Newton because he discovered them, of course, but sometimes other scientists at the same time did parallel the same, they discovered the same effects in nature, they formulate the same laws, and so we should also mention them. And Leibniz was also a computer scientist, and now you think, why can he be a computer scientist in the 17th century? But it's true, he built famous, let's say, computers, calculation machines, and they were mechanical calculation machines, and he used them for fluid dynamics simulations. Here again you see a pipe system, and here you can imagine that the height pressure, ρ times gravity constant times height, is important. If it is a pipe that goes with 10 meters of length, you will have a big pressure. You will have a big pressure difference from the top to the bottom, and then the water can flow outside, if you open it here at the exit. But if you closely look at this simple pipe system, you will see also elbows and armatures and different pipe diameters, and all this constructional let's call it features, cause a pressure drop inside the fluid. And this pressure drop, it is a loss of energy, so you have to look a bit closely at Bernoulli's law, and you have to formulate it a bit different. You have to add a loose term to the energy equation, and that's what we now want to do. And it gets a bit more complicated to explain it. You have the armatures, of course, you have the valves, you have the changes of the diameter, and all these armatures or valves cause a pressure drop. So we need a term for this kind of pressure drops. But we will have also an additional pressure drop, and this pressure drop is caused by the roughness of the walls. If we have, in the last chapter I teach you something about smooth walls, and also in ANSYS CFX we only did calculations for smooth walls now. But if you look closely at the walls of a pipe system, for example, you can have concrete in a wastewater system, and then you see the walls can be really rough. You can have stones or edges on these pipes, and this roughness can also cause pressure drop. It can cause a loss of flow energy, and but there's something more I have to explain. It will only cause a loss of energy if we have turbulent flows. And now, what are turbulent flows? You can have laminar flow fields, where the fluid flows without any disturbance, without any big gradient in the velocities. But you can have also swirls and turbulences inside the fluid, and these swirls and turbulences will cause pressure drop if they interact with rough walls or any armatures inside the pipes. And here are some pipes. I made some pictures for you. Maybe you can refer to the slide to see it a bit better. Here are pipes for heat conduction systems, and you might see you have really rough walls here. You have sometimes roughness inside the pipe, you have roughness at the outer diameter of the pipe, and this is mainly for a better heat transfer here at this picture, but the heat transfer will also be better if you have turbulence, but it will cause also pressure drop. And here on the left side you see a pipe for heat transfer. You will have warm water, a mass flow of warm water that enters the pipe, and you will place this, let's call it a snail, or you will place this pipe inside a pot of cold water, for example, and then you can heat up the water. And if you look closely, maybe if the video is not good enough, look at the slides. If you look closely at this pipe, you can see there are small bumps inside this pipe, and they are made to force the turbulence inside the fluid flow. So you will get better heat transfer, but on the other side you will get more pressure drop, and you have to pay this pressure drop. It is expensive. Pressure drop always costs money. For example, you will need a bigger pump. You will need a more expensive pump if you have a pipe with a higher pressure drop. So you have to pay for it, and you need more energy to get higher pressures at the entry, because you will have higher losses in the system. So here you see it, a sketch of the elbow. Here you enter the water into this elbow system, and the flow will go around the edge, around the elbow, and after the elbow you will always have also turbulent regions where you see turbulence, where turbulence happens, and these regions will cause high pressure drops, and they will also cause, because there is a pressure drop, they will also produce regions of low pressures, and that's something I always try to teach you. Also Bernoulli's law acts in these small regions. If you have high swirls and high turbulence and high mixing velocities, the pressure will go down, and then you will sometimes have really narrow pressures in this region. In a normal water system you have around about 3 bars, but in this region you can have much lower pressures. And what happens if you have water and the pressure gets lower than 0? Will you have negative pressures? No, of course. Negative pressures do not exist if the pressure goes into the region of 0, and it goes lower than the saturation pressure, and the saturation pressure of water is really narrow. It's about only 2100 pascals. That's nearly 0 bar. And if the pressure goes lower than this level, you will have a new physical effect. You will have the effect of cavitation, and cavitation means you get bubbles, you get like holes in the liquid, and it will be filled with gas, and it will fill, for example, with water as a gas. You will see these bubbles, and that's an effect I want to talk about a bit later again, but that's a really important effect. So if you calculate pressures with Bernoulli's law and you get pressures lower than 0 in a region, it is not physical. Yeah? You can calculate this with Bernoulli's law, you will get this result, you will get negative results for the pressures. It can happen, it's only mathematics, but it is not physically true. In this region where you get negative pressures, the physics will change, and you will get an additional effect of bubble building. And that's something I have to look closely in the next slides. Okay, and always when I try to explain you something, I love to take CFD results, and there is a really interesting CFD result. It's called the elbow case. Maybe we do this exercise also in the CFX. That's a result from a famous open source CFD code called OpenFoam. I also give lectures in OpenFoam, and that's a really famous example. It's a so-called elbow example, and here you see some cold water that enters from the bottom, and there's a small pipe, additional pipe, and water enters from this additional pipe, and at the exit of the pipe, the exit of the elbow pipe, there will be a mixing between the red, the hot water, and the blue, the cold water, and you will see turbulence effects. And here in this simulation the mesh was not so fine, and you can't see any big swirls, but you see the mixing of the red colored water and the white colored and the blue colored water. And I always try to build up a bit. I'm a fan of building up these experiments, and what I did for you here, that was the first version of my model. I built a small channel with water and a small pipe, and I injected some ink, some with blue color, and if you look closely you can see how the ink enters the pipe system. But this was only the first version of the model. It was not so really sophisticated, so I built it. Here I also edit your movie, but I will not start the movie. You can find this movie also on YouTube and look at it in a much better quality on your own. But I also wanted to build an additional model, a second version of the model. I built it a bit more sophisticated, and also it was a bit mess to take the ink and inject the ink at a special position, and it was a bit difficult to do it. So I came to another idea. I injected cold water and hot water, and then I took an infrared camera from FLIR, and I made some movies of the heat. And if you take this infrared camera, you can really good see the injection and the mixing of the cold and the hot water stream. And if you look at the fourth time step or in the third time step, you even see swirls and turbulences inside the fluid. And this was a quite interesting result for me. And okay, and that's something we will also explain a bit better. But please take into account, if you have turbulence, if you have swirl, you will also have a pressure drop. Also, this turbulence effect, the swirls inside the fluid, they cause a pressure drop. Here also is the movie. I don't want to start it now for you, but because then we will interact with YouTube on a YouTube video, and this is not really cute. I think you can refer to the link, you can look at the QR code with your smartphone, and you can watch the video in much better quality directly on YouTube. Okay, so what is turbulent? What is laminar flow? Here is also a nice picture of a flow, and this is a small candle here, and this is the flame of the candle, and the candle flame will cause higher temperature of the air. It will heat up the air, and this will cause a rise and a temperature. This will cause a higher velocity, and the air flow will go upwards, because of the lower density of the fluid. And at the first time, if the fluid starts, the fluid flow will be really laminar. But after a while, after a defined length, the fluid will change and the flow will turbulent. And that's the same effect that happens also in this pipe I showed you before. First we have laminar flow, and after a special length, the flow will be turbulent. And if you then have turbulent flow, and after some time it will be laminar again. So you can change from laminar to turbulent flow. And there's also a really important number, a number you should never forget, the so-called Reynolds number. And the Reynolds number will tell you if a fluid is laminar. And there is a magic number 2320, and if the Reynolds number is below 2320, you will have laminar flow. So here, if we calculate the Reynolds number, and we can calculate the Reynolds number by the velocity times density divided by viscosity of the fluid, and if the Reynolds number is higher than 2320, we will have turbulent flow. So we have a number where we can calculate if the flow is turbulent or if the flow is laminar. Okay, and here is also I want to mention the scientist, the famous person that has formulated these laws, and it's Mr. Osborne Reynolds. He lived from 1842 to 1912, and here is his formulation of the Reynolds number. The Reynolds number has no units, so it is density times velocity times a characteristic length divided by viscosity. And what is this characteristic length? Difficult word. What is it? For example, if you have a ball, or if you have a round object like a ball, you will take the diameter of the ball as a characteristic length scale. And or if you have a pipe, if you have a pipe of a heater or a heat conductor, and the air flows from one side directly to this pipe, and over this pipe you will take the diameter of the pipe as a characteristic length scale. You can also formulate this for flying footballs, for example. You will take the diameter of the football. And now you can also calculate the Reynolds number around the ball, and if the Reynolds number is lower than 2320, you have a laminar flow around the ball, and if it is disturbed, you have a Reynolds sum higher 2320. And you will always have high Reynolds numbers if you have really high velocities of the wind, of the ball, or if you have big objects. But you will have lower Reynolds numbers if you have higher viscosities. For example, in honey you have lower Reynolds numbers than in water or in air. Okay. So, and here's also the Reynolds numbers can be used to calculate pressure drop, and that's the so-called Nicorazzi diagram. And in the first region of this diagram you have the laminar region here, and you can look, the laminar region is linear, and you can calculate friction and pressure drop with this diagram, and you will see if you get high velocities you will get here lower values for lambda. But if you look into from here is a 2320 position, and if you get higher Reynolds numbers here on the x-axis, you will get higher or lower pressure drops here, and if you get higher Reynolds numbers, you will get different pressure drops. I think that's a good explanation. You will see there are not only one curve now, there are not only one line, there are a lot of different lines for different pressure drops, and these lines depend on the roughness of the walls. Yeah. So if you have a really rough wall, you have another pressure drop than if you have a really smooth, flat wall. Okay, and that's how you use this diagram. And I made two lines inside. So if you want to solve an exercise, you first, for example, if you want to calculate the pressure drop inside a pipe, you first calculate the Reynolds number inside the pipes, and you know if it's laminar or if it's turbulent, and then you make here this line, this red line, and then you can look how rough our wall is, and then you can go to the y-axis and have a look at your pressure drops. Okay, so here it's some conclusion. So the pipe is somehow what we neglect in this whole calculation. So you can calculate pressure drops, you can calculate losses, but you will neglect any kind of boundary layer formulation. So you will not calculate boundary layers with this. So you will be not able to calculate boundary layers with this filament theory of the Bernoulli's law. If you want to go more into detail, if you want to learn something about boundary layers, you have to make a detailed CFD model with a good resolution of the mesh on the walls, and then you can make this more sophisticated simulations.